at the topic of the day. We're not going to get through all this stuff. I want to get through limits, infinite limits, and maybe some asymptotes stuff. And then that's probably about all we're going to get for today. This will probably take us a couple days to get through all this. So quick review. One-sided limits, right? We've talked earlier about this. We know that the definition of a two-sided limit depends on the existence and agreement of the one-sided limits. And we've talked about that a fair amount. I think you guys are probably okay with that idea. Okay, so let's introduce this new function, the greatest integer function. Okay, and this is typically the symbol we use for it, although there's other symbols that apply also. The greatest integer function outputs the greatest integer that's less than or equal to the input. Okay, and some other ways of saying this again are, we got this notation. A lot of times, like on Desmos or on your TI 84s, it'll be int for greatest integer function. Int stands for integer and greatest integer function, or it could be a floor function. Floor means you're rounding down. Ceiling function means you're rounding up. You're just doing kind of the opposite. Okay. So let's try. Just you tell me what are the outputs associated with these inputs. What's the greatest integer function evaluated at 3.7? No, what's the greatest integer that's less than or equal to 3.7? 3. Okay, agreed. How about what if I were to do greatest integer function evaluated at -2? Greatest integer that's less than or equal to -2. -2, isn't it? Yeah. Okay. How about what if I evaluated at -0.1? -1, not 0, right? How come? Well, we're always rounding down. It's like we're sliding a bead to the left on a number line, starting at this position until it encounters the first integer. Pretend there are knots at all the integers. Okay. It's going to hit, what's the first knot it hits? Well, it's going to slide left to -1 in this case, right? Okay, so what's the graph look like then? Well, it's just an infinite step function. That's what this looks like, right? Doesn't that make sense? Okay. If I input an integer, input 1, the output is 1. But if I input a value slightly bigger than 1, it's gonna round down to 1 until I get up to 2, and then the output bounces up to 2. Okay, so I just create this infinite staircase with closed endpoints on the left of each stair and open endpoints on the right. Okay, give me thumbs. Does that make sense? Okay, and we've seen this before, right? We saw this a couple years ago too. Okay, so now let's take that idea and let's do something a little more complicated with it. What if we want to define a new function f of x, which is the greatest integer function evaluated at x divided by x? So what are we going to get if we want to take the limit of this new function as x approaches 1 from the left? That would be a value like what? Yeah, 0.999, something like that, right? We're just to the left of 1. Okay, so what are we going to get when we try to evaluate this limit directly? What are we going to get? If I'm taking a value slightly less than 1 and inputting it, what am I getting on the top? Everybody agree I'm getting 0? Right? If I've got a number like 0.9, I'm going to round down to, and that's really all it's doing is rounding down to the next integer, right? So I'm getting 0 on the top. On the bottom, what am I getting? Okay, but what value am I approaching? Because when I evaluate a limit, what am I approaching? 1, yeah, right? So it looks like 0 over 1, which is exactly equal to 0. Okay, so the limit is 0. What if I approach 1 from the right? What's that going to give me? That's like 1 point something. 1 on top and what on the bottom? 1, yeah. So my output is 1. Okay, so that's telling me then the limit of this function as x approaches 1 is what? Doesn't exist. How come? Don't agree, yeah. Okay, let's try this one. What if we approach 0 from the left? What's that going to give me? I'm going to get negative 1 over, okay, 0, right. So it doesn't exist, does it? Okay. Can we say more than that? It doesn't exist, right? Which means what in this case? See if we can be more specific. Why doesn't it exist? What's the graph doing in this case, do you suppose, for the limit not to exist? Ashley's got an idea. What's it doing? Okay, by moving up, you mean moving way up maybe, right? Got maybe an asymptote there. So the function, remember, limits aren't defined at asymptotes, okay? If it's an asymptote and we're approaching 0 from a specific direction, then really, if it's an asymptote, and you're right, it is, okay? Really, there's only one of two things that could be happening. Either the ant is, as he approaches 0 from the left, he's shooting up towards positive infinity or down towards negative infinity, right? In both cases, the limit doesn't exist because infinity is not a satisfactory answer for a limit, right? But in a way, it kind of is helpful. The limit still doesn't exist, but it might be nice to know what the behavior of the function is there. They mean very different things, infinitely different things, right? So could we figure out, we know that we're going to get some kind of infinity here. The question is just, what flavor of infinity? How could we figure that out? Is it positive or negative, right? Well, what is, as x approaches 0 from the left, yes, it's approaching 0, but it never gets there, right? So what kind of numbers actually appear on the bottom? Very small. What sign? Negative, right? Because we're approaching 0 from the negative direction. So we get small numbers like negative 0.0001 or something like that, right? I'm going to call this, remember, this goes back, we talked a little bit about this. What do I need to put up there then? A negative, right? That superscript of minus is telling me, okay, yeah, it's approaching 0, but it's approaching from the negative direction. So this 0 minus acts like a vanishingly small negative number, okay? And is this ringing a bell? I mean, like we did this stuff beforehand, right? Before a break, a little bit of this, right? You vaguely remembering this? If I have a constant number divided by 0, this part right here, that part is giving me the infinity part. A number divided by 0 always corresponds to some infinite result. Now, what about the sign? Well, the sign is going to be that on the top and that on the bottom. Negative divided by negative is positive, right? So we get positive infinity. Okay, everybody agree? All right, how about this last one here? Let's look at this guy. So as we're approaching 0 from the right, what is the greatest integer function on the top going to be? It's going to be 0, isn't it? Okay. it's going to be 0. How about on the bottom? 0 from the right. Okay, so it's a 0 plus. Now, what in the world is that equal to? Is that indeterminate? Seems like it, doesn't it? When we took limits and we got answers that were 0 over 0, that was indeterminate. But that was different because in those cases, the number on the top and the number on the bottom were both approaching 0. And we just, and that obscured what the final answer might end up being, right? We ended up having to do a bunch more work to figure out what that was. Okay, and it would vary depending on which one is approaching 0 faster, which one is approaching 0 slower. It was all veiled behind a curtain that algebra opened for us. This is different because the bottom is approaching 0. Is the top approaching 0? No, it is 0, isn't it? You see the difference, right? The greatest integer function evaluated at any number greater than 0, as long as it's less than 1, is exactly 0. It's not approaching 0. It is 0. So what I actually have here is exactly 0 divided by a non-zero positive number, right? What is 0 divided by any number, regardless of how small? 0. That answer is 0. You see why? Okay. Because the bottom is not 0. It's approaching 0, but the top is 0, and therefore the quotient is equal to 0. Okay. Does the bottom ever get to 0? Never does, right? Because it's a limit. So I never actually end up getting a 0 on the bottom. I just approach 0. Okay. Let's just make sure that this all is consistent with what the graph looks like. Okay, well, it is, right? Let's look at this. So we got, as we approach 1 from the left, we got 0. As we approach 1 from the left, the ant thinks he's stepping on a y value of 0. As we approached 1 from the right, we got 1. Again, true. The ant anticipates stepping on a y value of 1. And therefore, there's a break in the function, and the limit doesn't exist because limits don't exist at breaks in the function, right? Does that make sense? Okay, how about as we approach 0 from the left, we got an infinite result. Yeah, we do. Look, the ant is climbing up towards infinity. So we're getting the right results here. As we approach 0 from the right, we got exactly 0, which is true. The ant anticipates stepping on a y value of 0. How about that? Okay. Make sense? Okay. All right, let's look at a couple more of these, some infinite limits. So how about this first one? We always want to try to evaluate directly first, right? So what do I get if I try to evaluate directly here? As x approaches 1, the limit looks like 3 over 0, which means what to us? What have we always said about that? If we get a number divided by 0, what's the answer? Doesn't exist, right? And it's true, it doesn't exist. Okay, we could maybe go further, though, by exploring the two one-sided limits to see if at least we get consistent behavior. So what happens if I approach 1 from the right? I'm getting positive 3 on the top. What am I getting on the bottom? What's 1 minus 1 plus? 1 subtract 1 plus, let's say. So I'm subtracting a number slightly bigger than 1 from 1. What's that leave me with? What's it going to be? 0 plus 1 minus 1 point something. You're on the right track, but like what's 1 minus 1.1? Oh, I get negative 0.1, don't I? So you're right, it's going to be 0, but minus, not plus. Okay, so true, the limit doesn't exist, but what could we say about that? What's the behavior there? Negative infinity. It's infinity because I have a zero on the bottom but not the top. And it's negative because of the sign conventions. Positive divided by negative is negative, right? So I'm getting a negative infinity. Okay, what about the bottom one? Limit of the same function as x approaches 1 from the left. So now value slightly less than 1. Again, I just get 3 on the top. What do I get on the bottom this time? 0 plus. Okay, good. Okay, so we know it's infinite because I get a 0 on the top but not the bottom. What's the sign this time? Positive. Okay, so can we say anything more about this limit than DNE? We can't because the behaviors don't match, right? One's positive infinity and one's negative infinity. So yeah, we know the limit doesn't exist, but we can't even say that it has some other consistent behavior. It's inconsistent. So that's about the most we can say. Okay, compare that to an example. Darn it, I kind of want to. Let's see. I kind of wish I had built in another one. Let's look at this guy. We'll go backwards a little bit. So what do I get here if I try to evaluate directly? Got 0 on the bottom, right? What do I get on the top? Do I get 0? I don't, do I? I mean, yeah, you guys are doing a bunch of math in your head here, but you don't, right? You don't get, so I know I'm going to get a DNE kind of situation, but let's see if we have consistent behavior. Okay, one thing that I think is helpful to do is if these things are easy to factor, it's easier to evaluate functions than functions that aren't factored. Because you were going through the process right there of plugging in 4, and I got to find the value of each term and then add them all up, right? Does the top factor? Are there numbers that multiply to positive 10 and add to negative 7? What are they? Okay. That's easier to evaluate, isn't it? Because now if I plug in 4, I just get a number times a number, which is easy to evaluate, right? So it always is a little bit easier. If you can factor them easily, these problems are easier to evaluate in factored form. Okay, on the bottom, we've got x minus 4 squared. Okay, so if we evaluate this, then as x approaches 4 from the right, what am I getting on the bottom? What's x minus 4 become as x approaches 4 from the right? 4 point something minus 4 is? Say it again, Aubrey. Okay, so what would we call that? 0 plus, right? Small positive number. Okay, so on the bottom, we're going to get 0 plus, and we're going to square it, right? On the top, we're getting, what, 1 times 2? Or negative 1, sorry. Negative 1 times 2. Agreed? Did I do that right? Okay. And so on the top, I get negative 2. What is 0 plus squared? 0 plus, isn't it? Right. Small positive number squared is a small positive number. So what's the outcome there? Negative infinity. Agreed? I get infinity from the numbers, and then the signs give me a negative coefficient. Okay. Let's do the same thing on the bottom. We've already got it factored. Say factor's the same, doesn't it? Now, if we're approaching 4 from the left, what am I getting on the top? Well, did anything change? Right. Whether I'm approaching 4 from the left or the right, doesn't that give me a -1 times a 2? So I get -2 on the top. That part stays the same. What about the bottom? What is x minus 4 as x approaches 4 from the left? Small negative, right? So I'm getting a 0 minus squared. What's 0 minus squared? 0 plus. Yeah, aha. So I get -2 over 0 plus. Well, that's negative infinity again. And so now what could we say about the two-sided limit? Negative infinity. It doesn't exist, but this time we can say something about it. From both sides, it approaches negative infinity. And so we get the consistent answer, negative infinity. Okay, which tells us something pretty cool. It tells us that at 4, we've got a vertical asymptote, and the function is doing something like that, right? Okay, so that is useful. Okay. Okay, how about this guy? These trig ones are good to struggle through because you got to get a little insight into how you deal with these things. Okay, so the limit of cotangent x as x approaches pi from the right. Now, I never remember what a cotangent graph looks like on its own, but we can always come up with it. What do we probably do with this cotangent function to make it easier to deal with? Okay, yeah, write it in terms of the basic trig function, sine and cosine. What is cotangent? Cosine over sine, okay? So we're taking the limit of cosine x over sine x as x approaches pi from the right. Okay, well, what's the cosine of pi? -1, isn't it? Cosine of pi is -1, right? How come? Think unit circle. Think unit circle. Where is pi on the unit circle? Right there, isn't it, right? Cosine is the x coordinate, which is 1 or -1, right? The coordinates at this point are -1, 0. Okay, good. So we get -1 on the top. Now, what about the bottom? What's the sine of x as x approaches pi from the right? Okay, so that's on the unit circle, it's tricky, isn't it? As theta or as x is approaching pi from the right, if the ant is walking on the unit circle, where is he as he approaches pi? What quadrant is he in? Yeah, he's in quadrant 3, isn't he? He's in here. Everybody see that? Right? Because like we're sweeping out angles starting here. So there's going to be pi halves, pi, 3 halves pi. So a value of x slightly bigger than pi is actually down here, right? The ant is taking his little bitty ant steps approaching that point along the unit circle in quadrant 3, right? Now, here's what's happening. You guys are conflating the idea of a graph with the unit circle. Okay, let's look at this in terms of a graph and just reconcile this. So on a graph, there's y, there's x. If I graph a cosine function, what's a cosine function do? Starts up here, doesn't it? Right? Starts up here and it does that. Agreed? Okay, so its value, what are we looking at here? We're looking at sine, sorry, not cosine, right? We're looking at the bottom, sine function. Sine function starts here, right? And does that. Well, at pi halves, that's right here, isn't it? So as the ant is approaching pi halves from the right, the ant is walking along the function this way, right? Towards a y value of 0, but you can see that the ant has a negative value there, doesn't it? Right? So you can see it if you think of a graph, that's fine, but you can also see it on the unit circle, because on the unit circle, the angles are slightly bigger than pi, and so they're in quadrant 3, shrinking back towards pi, right? Okay, so the sine function is the y coordinate. Well, what's the y coordinate going to be as we approach that point? It's not 0, it's 0 minus, right? The y coordinate, because I'm in quadrant 3 where both x and y are negative. Does that make sense? Okay. All right, so then we get, regardless of which graph you use, it doesn't matter. On the bottom, we're getting back a 0 minus. So what's the overall result then? A positive infinity. Yep. And if we look at a cotangent function, well, let's just do that. Let's just cheat and look at a cotangent function. Did I already? Yeah, I already loaded it up. Okay, so here it is. There's a cotangent function. Well, as we approach pi, pi is right there. Agreed? A little more than 3. Let's zoom in. Okay, there's the vertical line, x equals pi. Look where we are. As we approach pi from the right on our cotangent function, the ant is climbing up towards positive infinity. We got it. Okay. Obviously you're getting what's tricky about that, though, is the idea that it's the angle that's approaching pi from the right. Okay. The angle that we're plugging into the cotangent function. Okay. Give me 1 to 5 on that one. How are we doing? Okay. All right. Okay. I'll take that. Okay. How about this guy? What's this answer? Should be able to tell me pretty quick. 0. Yeah. Right? How come? But not the bottom, right? So it's 0. Yeah. We get, as x approaches 3 from the right or the left, it doesn't matter. That value I'm approaching on the top, I don't even need to be specific here. It's 0. I could say 0 plus, but it's 0 plus still approaches 0. On the bottom, I get a non-zero value. I get 9 minus 6 is 3. So I'm done, right? That's a type 1. That's an easy one. Evaluate it directly and we're done, okay? Okay, how about this one? If I try to evaluate this one directly, yeah, this one I do get 0 over 0, don't I? Does everybody agree? I'm going to get 3 times 25, 75, right? So this is more work. We need some more work here. What's more work look like? What are we doing here? Say it again. Okay, yeah, we need to cancel, right? This is a cancellation technique one. I got a rational function, so if I get an indeterminate form, it means factors are going to cancel, but I've got to factor it. What does the top factor into? Take the 3 out, and then I'm left with x squared minus 25, which factors into? Okay. On the bottom, we've just got x minus 5 as x approaches 5 from the right. Well, there's our cancellation, right? Okay, does it even matter that x is approaching 5 from the right? No. What value is it approaching? 5. When I evaluate directly, I just get 3 times 10 equals 30. I mean, we could say it's 30 plus, but who cares? We just want to know 30, right? The plus part is irrelevant. Okay? Are you getting the flavor of this stuff a little bit now? I mean, you have to kind of work through it and see the subtleties, but when you're kind of getting an idea, when is the plus or minus superscript useful? When you need it. Otherwise, you just abandon it. We don't need it there. We needed it there, right? Because we needed to know what were the signs of the zeros on the bottom to tell us what kinds of infinities we were dealing with. Okay. But we don't need it, and we needed it there, but we don't need it there or there, right? Those are problems we could have done before we even knew that a one-sided limit existed. Okay, we did that one. Okay, so let's go to this guy, right? And remember this problem? We said we'd come back to it. I promised you we would. And here we are. Okay, so this is Einstein's, one of his many, many contributions to physics, special relativity. He tells us that the relativistic mass of any object is given by its rest mass divided by the gamma factor, which is the square root of 1 minus v squared over c squared, where v is the velocity of the object relative to some reference frame, some point, let's say, and c is this constant speed of light. Okay. Well, as v gets bigger and approaches c, something weird is going to happen. Okay. So if I want to know what happens to an object's mass, how could I do that? What kind of instrument could we use here that we're becoming pretty familiar with? Einstein showed us that there's a limit, an ultimate speed limit in the universe, which is the speed of light. Nothing can travel faster than the speed of light. Right? Any object with mass can't actually, and we'll see why, can't actually ever go the speed of light. So what would I have to do here? If I try to plug in c, I get a nonsense answer. I get m naught, rest mass divided by 0, don't I? If I let v equal c, I'm going to get c squared over c squared is 1. 1 minus 1 is 0. I'm getting a 0 on the bottom, which we can't do. Okay, so I'm using a limit here, aren't I? Right? I'm going to take a limit. I'm going to take a limit as v approaches from what direction? From the left. We can't approach it from the right, can we? Right? Because v could never exceed c. C is the speed of light, and nothing can go faster than the speed of light. So it's impossible to approach c from values greater than c. Can't happen. We can only approach c from values less than c. Okay, so we would do this then, wouldn't we? We want to explore what's the behavior of the limit of m naught divided by the square root of 1 minus, not plus, 1 minus v squared over c squared as v approaches c from the left. Okay, well, if we evaluate that directly, what's it give us? Rest mass, which is some positive constant. Mass is positive, right? On the bottom, I'm getting the square root of what? 1 minus c minus squared over c squared. What is c minus squared divided by c squared? Man. It's okay. It's C minus squared divided by C squared. Here's a way to approach it. Here's another way we could do this. Not zero. Okay, let's. Okay, approaching 1. Look what we could do though. If I have a property of exponents here that might be useful. If I have a squared over b squared, isn't that the same thing as the quantity a over b squared, right? So I could combine this stuff and write this as square root, or m naught, divided by square root of 1 minus the quantity c minus over c squared. Well, what's c minus divided by c? 1 minus, okay? One minus squared. And what is 1 minus squared? Like 0.9 squared is 0.81, right? Okay, so what's happened if I've got a number very, very close to 1, slightly less than 1, and I square it, I end up with a number slightly less than 1 still, right? Okay, so this is equal to m naught divided by the square root of 1 minus 1 subtract 1 minus, what's that? 0. What's the square root of 0 plus? 0 plus, yeah. Isn't it, right? Square root of a very small positive number is just another very small positive number, right? Yeah. Agreed? Okay. Okay, how big is that? Some constant divided by 0 is? Mm-hmm. What's the sign? Can't work. That's why any object that has mass could never go the speed of light, because its mass would become infinite, right? And you can't push something with infinite mass. That would require infinite energy, which the universe cannot provide. So it's impossible. You can invest, like at Stanford, in their linear accelerator. I probably told you this before, but when they, at SLAC, when they pulse, they accelerate these little charged particles, and they've got the speed record for positrons, for anti-electrons. If you take a positron and you accelerate this, you take all the collective energy associated, it's like consistent with, or be equivalent to, the entire Bay Area, all that energy use being invested in this little packet of positrons. You can get them going pretty fast. The record, I think, is 99.999999997% the speed of light. But you can't, that's even then, like all that energy going into that tiny little packet, accelerating these things down a 3-mile long building, you can't go the speed of light because it's impossible. You can get close, get arbitrarily close, depending how much energy you want to spend, but you can't ever get there. Okay? All right. How about that? Okay, last thing, probably for today. And this is a biggie. We'll end up with a heavy topic, and then I'll let your brains kind of just relax after this one. So how do you know whether a function that is undefined at x equals c, but it defined for all other values in the neighborhood of c, has a hole or an asymptote, or neither? So in other words, if I evaluate a limit directly, is there a way for me to know if it's a hole or an asymptote? Well, we know when it's an asymptote, right? It's an asymptote if I get what result? If I get a number on top and what on the bottom? 0, okay? Is it a hole if I get 0 over 0? A lot of books say that it is, and usually in high school, it works out that way, but that is not necessarily true. if we evaluate the limit and we get 0 over 0, that does not guarantee it's a hole. It means it could be a hole, or it could be an asymptote, or it could be something in between. We don't know. It's indeterminate, right? Okay, so I guess a hole would be something in between. A hole would be a value it's approaching. So how do you know, right? We can figure it out. For tomorrow, we will figure it out.